Okay, finite math students, this is Mr. Lewitt. This is going to be my last video on linear programming and the simplex algorithm. We're going to just do a couple problems, maybe 3 problems if there's time. These problems do take a long time, so I don't guarantee that we'll get to 3 problems. We may just do 2 problems, but that's probably going to be enough, okay? Okay, so once again, just a reminder, this is my last lecture video on this particular chapter, the chapter on linear programming and the simplex algorithm. Okay, so up until now, we have done standard maximization problems. Here, hold on one second. Let me turn on my marker. We have done standard maximization problems where all the constraints are of the form, wait a minute, that's not very pretty, less than or equal to. That's really not pretty. Hold on a second. Let me, there we go. Okay, so in a standard maximization problem, all of the inequalities are of this form, less than or equal to. In a standard minimization problems, all of the constraints are of the form greater than or equal to. So in this part of the homework, we're dealing with problems that involve many different constraints, less than or equal to, greater than or equal to, and also just regular equality. Okay, those are called mixed constraint problems. Mixed constraint problems, okay? So let me just erase that and turn off my marker. Okay. So a typical example, oh, and by the way, in your book, the authors of your book use something called the Big M method in order to solve these problems. Okay, so what is Big M? Okay, it's called the Big M method. And M is just some very, very, very big number. It could be 1,000,000, 1,000,000,000, 1,000,000,000,000. You don't know exactly what it is. It just represents a really big number. M is a symbol. Big M is a symbol. It represents a very large number. So when you're doing a standard maximization problem, you're going to introduce artificial variables. Okay, and each artificial variable will have a coefficient of big M. And that big M represents a really big number. And the coefficient is going to be negative. And the reason why it's negative is because you really don't want to produce any positive amount of the artificial variable, because if you do, that will greatly decrease the objective function, which is not what you're trying to do. You don't want to decrease the objective function. You want to increase the objective function. Okay, let's go through an example. If you see an example of this, then maybe you'll understand things a little bit better, okay? Let's see. Okay, one second. Introduce slack, surplus, and artificial variables and form the modified problem. I'm working on problem number 86. Write the preliminary simplex tableau for the modified problem and find the initial simplex tableau. Okay, so let me read that one more time. Introduce slack, surplus, and artificial variables and form the modified problem. That's part A. Part B is write the preliminary simplex tableau for the modified problem and find the initial simplex tableau. That's part B. Part C, find the optimal solution of the modified problem by applying the simplex method to the initial simplex tableau. And finally, part D, find the optimal solution of the original problem if it exists. Okay, so let's get started. Maximize, okay, fill in the coefficients for all variables to form the modified problem. 6x1 plus 11x2 minus big M times the artificial variable, subject to 1x1, 1x2, slack variable, okay, that's a slack variable, no surplus variable, no artificial variable, and that's equal to 2. We don't need a surplus variable or an artificial variable for the first constraint because the first constraint has the form less than or equal to. Let's look at the second constraint. 3x1 plus 4x2. There's no slack variable. There is a surplus variable, which always has the coefficient of -1, and there is an artificial variable, and that's going to have a coefficient of 1 is equal to 10, and all of my variables are non-negative. Okay. Complete the preliminary simplex tableau. Okay, so we have, let's see, you know what, let me expand this. 1, 1, 1, 0, 0, 0, 2, 3, 4, 0, -1, 1, 0, 10. Okay, -6, -11, 0, 0. This will be positive M. This will be 1. This will be 0. Let's continue. Complete the initial simplex tableau. Okay, so here, okay, so we need to modify this table or matrix. Most people call it a matrix, sometimes it's called a table, but we need to modify this. Okay, hold on, let me turn on my marker. Okay, this column right over here, that column right over there has to become a basic column, which means it has to have the form of 0, 1, oh, hold on one second, 1, 0. Ugh. Okay, that's, let me try that one more time. Okay, so this column right over here has to become a basic column, which means that the A1 column, the column that represents the A1 variable, has to have the form 0, 1, 0. Well, it's a funny looking 0, but it's supposed to be a 0. Okay. Let's see, hold on one second. Okay, there we go. So let's do that. matrix 1 1 1 0 0 0 2 3 4 0 negative 1 1 0 10 negative 6 negative 11 0 0 m 1 0. Okay, so we need to oh, 1 second, what did I just do? Okay, we need to, oh, hold on just one moment. Hold on a second. Okay. We need to replace this m with a 0. All right. So we're going to modify the third row. Minus m times the second row, because the second row contains that magic 1, right? Let's expand my result so it's easier to read. Oh, of course. Okay. Foolish me. Why am I calling it matrix A? Foolish. Okay. 3 is equal to matrix 3 minus m times matrix 2. Let's make it look a little bit nicer. Okay, well, that's a little bit nicer. Okay. So, a little easier to read. Okay. So we can see now that this column is basic. Let's hope it stays. Let's hope that it stays that way for most of our problem, okay? Because otherwise, there's not a solution. So we have 1, 1, 1, 0, 0, 0, 2, 3, oh, 1 second, 4, 0, negative 1, 1, 0, 10, negative 3m minus 6, negative 4m minus 11, 0, m, 0, 1, negative 10m. Okay, what is the optimal solution of the modified problem? Select the correct choice below and fill in any answer boxes present in your choice. Okay, so where should we start pivoting? We need to start pivoting in this column, okay, because negative 4m minus 11 is the most negative number in the bottom row. So 2 divided by 1 is 2, 2 divided by 1 is 2, and 10 divided by 4, that would be 2.5. So 2 divided by 1 is smaller. We're going to pivot right over here. We're going to pivot in the first row, second column. Or you could say, we are going to pivot in the second column of the first row. 2 is equal to matrix 2 minus 4 times matrix 1. Let's see, traditional form. Okay, why do I keep doing that? Okay, because usually I call my matrices A. That's a little weird. Okay, let me, okay, let me get rid of that. So, matrix, traditional form, matrix form. There we go. Matrix 3 is equal to matrix 3 plus 4m plus 11 times matrix 1. Yeah, I usually call my matrices A. That's why I keep typing A. So don't let that confuse you. Okay, traditional form, matrix form. Okay, we need to expand it. Matrix is equal to expand matrix. And the reason I'm doing that is because there are algebraic expressions in the bottom row. So matrix, traditional form, matrix form. Okay, so this is what we have. The problem here okay, so the problem that I see here, there are no negative values in the bottom row. There are no negative values in the bottom row. So remember, m is a very big positive number. So this value is positive. Oh, excuse me. This value, can't seem to highlight this quite right. So this value is very positive. This is positive. This is, of course, 0. Positive. Okay. So the problem is the artificial variable right over here, the artificial variable is equal to 2, and that's not good. So what I have here is x1 is 0, x2 is 2, s1 is 0, okay, wait a second, x1 is equal to 0, x2 is equal to 2, s1 is equal to 0, s2 is equal to 0. The problem is a1 is equal to 2 and p is equal to 22 minus 2m. What is the optimal solution of the original problem? So here we have a real issue. Number one, p, the objective function, contains an m term, and the value of a1 should be 0, but it's not. Therefore, there is no optimal solution of the original problem. It's not solvable, okay? Not all of these problems have answers, by the way. So that wasn't so terrible. That wasn't so terrible, right? Let's do another one. Okay. We could do 87. We could do, let's do 88. 88 maybe is a little more challenging than 87. We could do 87, but 88 is a little longer, so okay. Clear matrix, which simply means I'm starting over again with a brand new matrix. Okay. So it says here I have to maximize P is equal to 2x1 plus 6x2, and these are my constraints. These are my constraints. So let's write this down. Let's write this down. Writing assistant, text cell, frame it, okay. Well, let's see, hold on a second. So this is problem number 88. Let's make this a little bigger. Problem number 88. Okay, so P, we have to maximize P is equal to 2x1 plus 6x2. These are my constraints. x1 plus 2x2 plus slack variable 1 is equal to 20. 2x1 plus x2 plus another slack variable is equal to 18. This is a greater than or equal to constraint. It's different. x1 plus x2 minus s3 plus an artificial variable is equal to 11. And I'm going to have to modify this function with minus m a1, or my first artificial variable. Okay? So this is the modified problem. And of course, remember, all variables must be greater than or equal to 0. That's good enough. Okay. So let's start it. Let's start the process of solving this problem. Matrix is equal to 1, 2, 1, that's S1, no S2, no S3, no artificial variable, and we're supposed to have a column that represents, you know, the P function, the objective function. 20, 2, 1, no S1, S2. Let me start that over again. 2x1, 1x2, no s1, yes there's an s2, no s3, no artificial variable. We have that extra column for the p function, 18. The bottom row, oh, we haven't even gotten there yet. Okay. So, 1x1, 1x2, no s1, no s2. We have s3, an artificial variable. Again, we need that extra column for the p function. bottom row is negative 2x1, negative 6x2, no s1, no s2, no s3, no a1. No, there is an a1. The coefficient is m. And we do have the 1 that represents the objective function p, and then 0. Okay. So let me just make sure this looks okay. So we have x1, and the way to do that, actually, I could do this. Prepend matrix x1, x2, s1, s2, s3, a, p, resources. Okay, so this is the x1 column, x2 column, s1 column, s2 column, s3 column, the a column, the p column, the resources column. It looks good. Okay. So the first thing is we need a 0 over here. Okay, the artificial variable has to start out being basic. That's easy. It has to be a basic variable. The artificial variable is supposed to be initially a basic variable. So we are modifying the 4th row of the matrix. And where is the 1 in the column? That 1 in the column is in the 3rd row. Okay. Okay, this looks good. So the most negative value in the bottom row is this value, negative m minus 6. Okay, so 20 divided by 2 is 10. 18 divided by 1 is 18. 11 divided by 1 is 11. 20 divided by 2 is 10 is the minimum ratio. We have to pivot right over here. So the first row, okay, the new first row is 1/2 times the old first row. I'm using traditional form, guys, because we have algebraic expressions in the bottom row of the matrix. Excuse me. I'm using traditional form and also the expand function because we have algebraic expressions in the bottom row of the matrix. So if I did not use expand and if I did not use traditional form, the matrix would still print. It would still print to the screen, but it would be more difficult to read. Okay. Second row. We have to change that second row. Change that third row. And finally, we have to put a 0 here in the bottom row so that this column represents a basic variable. think we need to expand this a little bit. Okay, let me see. Are there any negative numbers in the bottom row? Yes, right over here. 1 minus m over 2. Remember, m is a very large positive number. So 1 minus m over 2 is a very large negative number. Okay, so let's figure out those ratios. 10 divided by 1/2 is 20. 8 divided by 3/2. Let's see. It's 5.3333. And 1 divided by 1/2 is 2. Which one is the smallest? It's this one right over here. That's the minimum ratio. So 10 divided by 1/2 is 20. 10 divided by 1/2 is 20. 8 divided by 3/2 is 5.33333, and then 1 divided by 1/2 is 2. We have to pivot right over there. Okay. The first column of the third row. Okay, so 2 times matrix 3. Matrix form. Change that first row, minus 1/2 times the third row, so remember, why am I doing that? I'm changing the first row. The new first row is equal to the old first row minus 1/2 times the third row, because the third row contains that magic 1. And then we'll do the same thing to the second row. And then finally, we need a 0 in the first column of the last row. Okay, let's do an algebraic expansion. Okay. Okay, so this actually looks really good. This column here represents the artificial variable. We can see that it's non-basic, which means the value is 0, which is really good. So the maximum value of P is 58 when x1 represents the value 2, and x2 represents the hold on a second. X2 represents the value 9. So once again, let's go over this. This is the final matrix. This column right over here represents my artificial variable. It's non-basic. It's non-basic, which means that by default the value is 0, which is good. That means there is a solution to the problem. This is my x1 column. x1 represents the value of 2. This is the x2 column right over here. x2 represents the value of 9. Let's see if this works. x1 is equal to 2. x2 is equal to, x2 is equal to 9. 2 times x1 plus 6 times x2, it's 58. x1 plus 2x2, is it less than or equal to 20? True. 2x1 plus x2, is it less than or equal to 18? True. x1 plus x2, is it greater than or equal to 11? True. Is x1 greater than or equal to 0? True. Is x2 greater than or equal to 0? True. Is x3 greater than or equal to 0? True. Oops. Oh, we don't have an x3. Sorry about that. Okay, just x1 and x2. Okay, so this should be the correct answer. Okay, that's it. These are mixed constraint problems. I'm not going to put them on your quiz or your test, okay, because for some people they are very, very challenging. However, you should be exposed to it. You should be aware that such problems do exist in the world of linear programming. Linear programming actually gets very, very complicated. It's a very it's a very complicated branch of higher mathematics. Linear programming is actually part of something even bigger called operations research. Some people call it operations research, some people call it industrial engineering, some people call it management science. It's all the same thing, but linear programming is a part of that. And it's actually very important. It's very, very important. So yeah, you should be aware of it. You should know what linear programming is, because people in business and finance and economics really do use linear programming models to represent data. Okay, so it's good to, you should be exposed to this. Even if this is not something you use every day, you should be exposed to it, and you should know what it is and what it is used for. Okay? Alright guys, I think that's going to be enough for today. This is my last video lecture on this homework assignment. If you have questions, feel free to email me and I will try to help you out. Okay, take care and have a great day. Bye-bye.